Hello everyone. So today we are going to discuss one of the applications of visible light communication, which is LiFi Wi-Fi coexistence, which means both LiFi and Wi-Fi will coexist, and you will see during the course of the lecture that there is a improvement in the performance. So let us discuss some of the advantages of LiFi over RF. It is license-free optical spectrum, unlike RF where one has to pay for the spectrum. And since this is being visible light communication, there is no license required for optical spectrum. The ability to be used in RF restricted areas. We cannot use RF in, for example, in hospitals or underwater. In hospitals, it might interfere with some of the machines which are sensitive to electromagnetic radiations. Underwater, the RF losses are very, very high. So we cannot use, RF technology in hospitals and underwater. So whereas the VLC or optical communication or the light communication can be used in hospitals and underwater. The LiFi or light communication is secured in the sense that the light does not penetrate opaque objects. So the light is confined inside the room. It does not go outside. So LiFi or VLC communication is more secure as compared to RF or Wi-Fi communication. LiFi has some limitations. It covers a relatively short range, usually few meters, with single AP. AP is access point. It is susceptible to connectivity loss due to obstruction. So whenever there is a obstruction between the source and the receiver, there may be loss. There may be, there may not be any signal between transmitter and receiver, so there will be obstruction. For example, this is your TX and this is RX. Essentially, this is a line of sight technology. So if there is a obstruction here, it will be blocked, the light will be blocked and you will not get anything at the receiver. But if you combine both Wi-Fi and LiFi, it's a promising technology to fulfill the future demands of data rates. It can offer you performance which is required for beyond 5G and IoT applications. So there are various types of hybrid networks. Suppose a user is in outside environment, he is connected to either a macro cell or a micro cell, cellular part of cellular communication. As he moves and if he happens to be below a lamp, then he may be connected with LiFi. And as soon as he enters a building, you have both LiFi access point and Wi-Fi access point, or there could be a femtocell inside. Then this combination of LiFi and Wi-Fi or femtocell will give enhanced performance. So these are some of the examples of hybrid networks where the light communication and RF communication, they coexist. Now, system design is very important in such coexistence scenario. So the deployment of LiFi and Wi-Fi access point is of vital importance to the network performance. And we need to ensure that LiFi also meets the illumination requirements. So the light intensity has to be such that it meets both illumination requirement as well as communication requirement. Then resource allocation. Load balancing is critical for hybrid LiFi Wi-Fi networks. Since Wi-Fi, if there are many users accessing Wi-Fi access point, it may result into some overload. So one has to do intelligent resource allocation between the LiFi access point and the Wi-Fi access point. User mobility is a matter of concern in coexistence, because in LiFi, it is relatively a short coverage range, and if the user moves even with a moderate speed, there will be frequent handovers from one LiFi to another LiFi. So one has to be careful while designing a system so that these frequent handovers are avoided, because each handover will result into some overhead which may decrease the throughput of the system. LiFi channels are subject to light path blockages, and also the receiver orientation. Suppose it is a mobile, the mobile is not always facing the luminaire or the light or the transmitter. So it may be at some angle. So one has to take care of this receiver orientation. It may affect, the performance. So LiFi channels are subject to light path blockages. This is because any obstruction coming between the line of sight will obstruct. And also the receiver orientation is continuously changing. So one has to take care of this receiver orientation by having, sometimes angle diversity receivers, where you have receivers at different angles mounted there. And then whenever the device is, changing the orientation, one of the receivers is getting light. So this is how this can be handled. Receiver orientation can be handled. So hybrid LiFi Wi-Fi networks can not only improve the network performance in terms of throughput and latency, but also benefit. It gives you indoor positioning. You are able to find out the accuracy, the position accuracy. I mean, you are able to find out the positioning of the objects using VLC or using different optical transmitters which are there in the room, and also it increases physical layers security. So there is improvement in the performance in terms of throughput and latency, but also you are able to find the accurate position of the objects and also enhanced physical layer security. So this is a typical diagram of a hybrid LiFi Wi-Fi network. So you have, these are the, for example, laptop devices, and there is a dongle here, LiFi dongle, and Wi-Fi is part of the laptop. So this is the dongle, the red strip you see is the dongle here. And then you have, these are the LiFi APs, access points, and also you have Wi-Fi access point inside the room. So the important thing here is, how do you associate user to different access points? How do you allocate the resources which are from LiFi access point and Wi-Fi access point? So there is a hypervisor required to allocate, resources and appropriate association with the access point. And this is done using software-defined networking, SDN is software-defined networking. So basically, SDN decouples the data and user plane, and a SDN agent will extract the information and convey the information to the SDN controller, which will direct flow routes of the packets. So this is how a typical hybrid LiFi Wi-Fi network works. There are various design considerations while designing the LiFi Wi-Fi architecture. The one is network architecture, which I have just discussed, using SDN, software-defined networking. And then how your cells are deployed. For example, in cellular, you have different options. One is this hexagon, which is very popular in cellular deployment, and then you have lattice kind of deployment, and then you have Poisson point process, which is some random deployment of base stations. Poisson point. In LiFi, hexagon may not be a suitable option because you also have to worry about the illumination part, whereas the lattice may be a good solution for VLC transmitters, deployment on the ceiling, because it can give you uniform illumination throughout the room. And Poisson point process may not be a good option for LiFi deployment. And then there are various kind of multiple access scheme, the simplest being TDMA, time division multiple access, or if you're using OFDM, OFDMA, orthogonal frequency division multiple access, or NOMA, non-orthogonal multiple access, or standard says CSMA, CA, carrier sense multiple access, collision avoidance. So these are some of the options of multiple access schemes we used in LiFi. And there are a lot of modulation techniques which can be used, starting from baseband digital modulation. This we had covered in the course also, baseband digital modulation. For example, PAM, pulse amplitude modulation, pulse position modulation, or variable pulse position modulation. These are some part of the standards. Or you can have color based on CSK, which is color shift keying. We had a detailed analysis of color shift keying. And we also discussed about optical OFDM. Under this head, we had discussed about DC OFDM and ACO OFDM. These are different variants of optical OFDM. So there are various techniques available, and all these techniques have been studied in the literature. And then you have to maintain some illumination requirement, because each place requires different kind of illumination. A factory where you handle very, very small objects may require good illumination. Office may require certain other type of or certain other value of illumination. So one has to keep in mind for which application the system is being designed, and one has to ensure the illumination part. And then one has to worry about the backhauling, how the information is backhauled to the network. So these are some of the design considerations for LiFi, Wi-Fi hybrid networks. So this is an example of a multi-access mechanism where I have shown TDMA and OFDM, which are quite popular. So in TDMA, the whole bandwidth is allocated to the user, and it is given in some time slot, for example, slot number 1, and then it is given in the slot 2. In a different slot, the whole bandwidth is given to user 2, and so on and so forth. And there is some guard band between the two slots. And in OFDMA, you divide the whole bandwidth into subchannels, or they have the subcarriers, and the subcarriers are allocated to the user. So it is depending upon the requirement of the user, you allocate resources or number of subcarriers to the user, and there is some sort of guard band so that there is no interference between subcarrier 1 and subcarrier 2. So these are the two examples of multiple access mechanism: time division multiple access and orthogonal frequency division multiple access. The performance metrics which are used in such networks, in such hybrid networks, is coverage probability. This basically is defined as probability. This S stands for, say, SNR. Probability that S, the signal to noise ratio, is greater than some threshold. And this alpha, beta, gamma are the angles of the device, because it also depends on the orientation of the device. So this is the orientation is defined by these three angles, alpha, beta, and gamma. So the coverage probability is defined as SNR greater than SNR threshold given the orientation of the device. The second is fairness. And this fairness is defined as I is equal to summation I is equal to n xi whole square divided by n summation I is equal to 1 to n xi whole square, where n is number of users and xi is average data rate of the user. So it basically tells, this number I tells how the data rate is divided among the users. If everybody gets same data rate, the fairness of the system is 1. So the limits of fairness, or the limits of I, is actually between 1 by n and 1. This is a range. If this value is 1, that means every user is getting similar amount of data rate and the system is called fair. This is a fair system, most fair system. If somehow all the resources are given to one user and others they don't get anything, then the value of the fairness is 1 by n, which is the least value. So the system is not fair at all. So one has to ensure that this I, value of I, should be as close to 1 as possible, so that all the users get fair amount of data. The third, this is also called as Jan's Fairness Index. Jan's Fairness Index. There are other definitions also, for example, Max-Min fairness or quality of experience fairness. But in literature, Jan's Fairness Index is used quite often. The third performance metric is spectral efficiency. Spectral efficiency is actually what is the bit rate per unit hertz. So it is defined as how many bits per second you are able to transmit in a given bandwidth. The units are bits per second per hertz. So this is spectral efficiency, another performance metric which is evaluated in such networks. Then another important unit is area spectral efficiency. Now, area spectral efficiency, actually, if you see VLC, it has a footprint which is called as attocell, and there are many attocells inside the room because there are many, transmitters. So you can reuse the resources, bandwidth resources in each cell. Reuse. So if you are, because the attocell is very small and you are able to reuse the resources, then the spectral efficiency, if you define per unit area, is also an important parameter. So for visible light communication, area spectral efficiency, which is defined as R, which is the data rate of the system data rate, and AR is the area of the indoor environment. So area spectral efficiency, when you have both LiFi and WiFi, makes better sense as compared to spectral efficiency. So that is why in hybrid networks, area spectral efficiency, or also called as ASC, is important. So now let us try to understand this LiFi coexistence, and let us draw the system model which we are going to study. So system model, suppose you have a room. This dimension can be, say, -20 to 20. This is 0, so about 40 meters, or it can be, 10 meters or some other dimension. And it has RF APs and VLC APs. VLC access points. So VLC I am denoting by, for example, these crosses. These are the optical transmitters or the illumination source inside the room. So these are VLC APs. And RF APs, for example, inside this room I have 4 RF APs. So this is RF APs. And then users are, let me make a bigger circle here. And the users are uniformly distributed inside the room. These are the users which are uniformly distributed inside the room. So we will need to calculate the average throughput and the outage performance. So we will try to evaluate this average throughput and outage performance and see that as compared to standalone LiFi or standalone Wi-Fi, this coexistence of LiFi and Wi-Fi gives a improved performance. So in the analysis, we will consider the downlink only, downlink, that is from transmitter to receiver. We will evaluate this performance. And we will assume that user is associated with the AP from where it gets a higher signal, associated to the AP from where it gets higher signal. And if there are many users which are coming in the ATO cell, for example, this is ATO cell, and there are many users coming here, which is associated with this LED or this transmitter one, then to avoid interference, it will use a TDMA scheme, which is based on round robin scheduling. So each user will get access to LED 1 for some time slot, and then it will go to the another user which is in the same auto cell. So we'll assume that it follows within the auto cell TDMA protocol, which is round robin scheduling, and all the VLC use the same bandwidth. All the VLC use the same bandwidth. So there may be CCI, co-channel interference. So these are the assumptions we are making while evaluating this model. Maybe there will be co-channel interference, CCI. So regarding RF APs, this was about VLC AP. Regarding RF AP, we will assume that BR is the total bandwidth and PR is the total power. And we are assuming that there are 4 RF APs, and PR is the power and BR is the bandwidth of the RF AP. And also there is a central control unit, CCU, central control unit, which controls VLC and RF system. So this particular device, CCU, controls both VLC and RF devices, and it is known that RF spectrum and VLC spectrum, they don't overlap. So there is no question of interference from RF source to VLC access point or VLC access point to RF, because their spectrum is entirely different. So let us discuss 2 scenarios while evaluating the performance of hybrid network. One, let us call it as the D1 scenario. In D1, each RF AP access point gets 1/4, assuming there are 4 RF APs inside the room. Each RF AP gets 1/4 of the bandwidth and 1/4 of the power. The total bandwidth is BR for all the APs and total power is PR. But in one scenario which we are considering, each RF AP will get 1/4 of the bandwidth and 1/4 of the power. And there is a uniform distribution of users. Uniform distribution of users on the inside the room. And also let us assume that RF APs are symmetrically placed. The other scenario, D2, could be where this central unit or central controller unit, CCU, central controller unit, it dynamically splits the spectrum and the power depending on the traffic. Spectrum and power depending upon the traffic. Instantaneous traffic. So for example, if all the users are near RF1, RF access point 1, then the total bandwidth and total power is given to that particular AP. If there are less number of users, then it is given to some other AP where you have more number of users. So it basically dynamically splits the spectrum and the power depending upon the instantaneous traffic, depending upon how users are located inside the room. So these are the 2 scenarios which we will try to evaluate. So now let us start modeling the VLC system. So the channel gain, this HS channel gain, this we have done many times. Channel gain is given by this expression where M is the Lambertian parameter. AD is the area of the PD, area of the receiver. This is TS theta is filter gain. This is concentration gain, concentrator which are using at the receiver. And this D is the distance between the TX, distance between TX and RX. And this theta C is the FOV of the receiver. So just to tell you what are these phi and theta. So you have a TX here, a receiver is somewhere here. This is the line of sight, which the distance is D. And this is, for example, the FOV. So let us draw the normal here. So this is half of the FOV. So this is theta C by 2. And draw a normal here. This angle is phi. And this angle which it makes is theta. So this channel gain is given by this expression. This we have done many times when we were discussing indoor channel modeling. And of course, G theta, which is a concentrator gain, depends on the refractive index of the concentrated sine square theta C. And this theta has to be between theta C and 0. This value is 0 if it is. If theta is greater than theta C. So if I calculate the SNR IK, where I is the ith user, this is ith user, and K is the VLC access point. So SNR between the VLC access point and the ith user is given by gamma HIK PV whole square, where gamma is the responsivity. This is the channel gain between the kth access point, VLC access point, and ith user, and P is the power of the VLC transmitter. This is the noise part, where N0 is noise PSD, power spectral density, units are ampere hertz, and this is the interference term. It is coming from all other sources. This is L is equal to K. So other than K, for the other sources in the room, other VLC access point, this is the interference term, where HIL is the between the user IE and the Lth VLC AP. So this is the interference term. This is the interference term. So if I calculate capacity of the ith user is given by B by 2 log 2 1 plus SNRI. Now this B by 2 is coming because I am using OFDM modulation technique, and in OFDM modulation technique we have studied that the half of the subscribers are conjugate of the other half, because we need to maintain the Hermitian symmetry. We want to make the signal real and unipolar. So only half of the subcarriers are carrying data. So that is why you get a factor of half here. So the rate becomes B by 2 log 2 1 plus SNRI. And this SNRI is actually maximum of SNRI K. So there are K VLC access point. So the user will be associated with the VLC, which gives the maximum SNR. So this SNRI is actually maximum of SNR IK. And if there are many users which are a part of the single ATO cell and connected to a single VLC AP. In that case, the rate is given by B divided by 2. This is coming because of the OFDM, and this is the number of users. So this is number of users which are connected to VLC access point K. And there may be many users, and we have discussed earlier that if there are many users, to avoid interference, we follow a TDMA protocol for these users with RR, with the round robin scheduling. So this is the expression for rate when there are more than one user inside the ATO cell, and this is the rate when there is only a single user inside the ATO cell. Now let us discuss about the RF system. So let us assume that RF system is millimeter wave, where the frequency is 60 gigahertz and majorly line of sight. And as I mentioned in the system model, we have used 4 APs, RF APs. The idea is that the user should be connected to a AP which has the shortest distance so that he gets maximum SNR. And the other could be if there is some blockages or some obstruction between one of the RF AP, the user gets signal from other RF APs. So there is some sort of diversity built into the system. So that is the whole idea of using multiple RF APs. So the link probability, so let me write this, link probability is high and the distance is low because the user will be connected to the nearest RF AP so that you get high SNR. So that is the idea for using multiple APs. And also we are assuming that same as VLC, we are using OFDM modulation in the RF also. So as far as the modulation is concerned, for both RF and VLC, we are using orthogonal frequency division multiplexing. So if I calculate the channel gain between kth RF AP and ith user for the nth subchannel, so this denotes the subchannel because there are subcarriers. This is given by, which is written here as HNIK. Once again, this is a channel gain between the kth RF AP and the ith user for the nth subchannel is given by root 10 raised to minus L dik divided by 10 HWNIK, where this is normalized channel gain. This is normalized channel transfer function. And LDIK, let me write here, this is important, LDIK is large scale feeding loss in dB. And this LDIK is given by this expression where L0 is reference path loss at distance 1 meter path loss at D0 distance, which is actually 1 meter, and this is roughly 68 dB. And this alpha which you see here is path loss coefficient, path loss exponent. And this xi k is used as shadowing component. So shadowing component. This is the distribution is Gaussian here for this, Gaussian with zero mean, and standard deviation is of the order of 1.8 dB. So this is how LDIK, the loss at distance, DIK is defined. That is, it consists of a reference path loss plus the, because of the path loss component, and then there is a shading component which is Gaussian distributed with zero mean and standard deviation 1.8 dB. I can take HIK as I. So first of all, let us see HIKN is HIK, because I am assuming the loss of the channel will be same for all subchannels. The optical wireless channel is a flat channel for different subchannels of the OFDM signal. So I can equate this HIKN, it is independent of frequency, is HIK. And this HIK can be approximated as HI, because you are taking the largest signal from the RF AP. So it is nearly equal to HI in all the cases. So the rate tau I is given by delta B, and delta B is the subchannel bandwidth. This is subchannel bandwidth. And this is a power in the subchannel I, power in subchannel I. And HI is the channel gain, and this NI is the number of users, number of rather subchannels allocated to the user N, user I. So this is the rate. It will be sum of N going from Ni up to Ni. So basically Ni is number of subchannels allocated to the user I. And delta B is the subchannel bandwidth, and delta P is the power in the subchannel. And N0 is the noise PSD. So this is for the case of RF, this is the rate. Now let us discuss the two scenarios which we have discussed earlier, which we had called as D1 and D2. So in D1, the resources are divided equally among all the RF APs. And so for this case, D1, the rate will be BRI divided by URK log 2, 1 plus HI mod square PRI divided by N0 BRI, where this is the power and RF power, and this is the bandwidth or the spectrum. And this is the number of users to the kth RF AP. So this is the rate. And another case which is D2, where the central unit or CCU dynamically allocates resources depending upon the instantaneous traffic requirement. So let us assume that all the users are linked to one particular RF AP, and it gets the full power and full spectrum. And if they are distributed among, say, for example, two APs, then half of the power is given to RF1, the other half is given to RF2, so on and so forth. So I'm assuming a case here where the total power, all the users are connected to RF AP, single RF AP, and the total bandwidth is given to that particular RF AP, and total power is given to that RF AP. So for that case, the rate is given by BR divided by UR, where UR is summation of all the users. Log 2, 1 plus HI mod square, PR divided by N0 BR. N0 is the noise PSD. So HI is modeled as, for the millimeter wave propagation, is given by HI is equal to 10 to the minus L dik by 10, where L dik we had defined earlier, which has the reference component and the path exponent component, and the third one was shedding component, into root k 1 plus k HDI plus root 1 plus 1 plus k HSI, where this k is the Riccian factor. And HDI is actually is 1 by 2, 1 plus j is a complex number, and it's a direct path fading, and this HSI is given as complex, is a normal Gaussian function with 0 mean and variance 1, and this is scatter, the component which is scattered path fading. So this for millimeter wave, this is the expression for HI. And the VLC parameters which have been used in the system is area we have taken 10 into 10 meters square, and the PVLC per VLC power is 9 watts. The bandwidth of the source is 40 megahertz. The area of the detector is 1 centimeter square. The irradiance angle is 60 degree. This is the transmission or emergence angle from the transmitter, irradiance angle. And this is the filter gain, which we have assumed as 1, and FOV as 90 degree field of view for the receiver. This is the refractive index. This is used when we calculate the gain because of the concentrator. It is equal to n square divided by sin square theta c. So n is the refractive index of the material of the concentrator, and this is the responsivity 0.5 amperes per watt. And the noise spectral density is defined as 10 to the minus 21 ampere square per hertz. So these are the VLC simulation parameters. So now let us discuss the simulation results based on the parameters which we have discussed in the last slides. So I will plot these simulation results for 3 scenarios. One is where you have only LiFi standalone in the room. There is no Wi-Fi standalone. The second scenario is D1, where the resources are allocated equally to all the APs, RF APs. This is D1 scenario, which we had discussed earlier. The third one is D2 scenario, where you dynamically allocate power and spectrum resources to the RF APs, depending upon the instantaneous user requirements. So we will try to compare these 3 scenarios. So let us draw a plot between, say, this is average data rate, megabits per second. So this is 0, this is 30, this is 50. And this is, on this y-axis is CDF, that is cumulative distribution function. So for LiFi standalone, this is something like this. For D1 scenario, it will be something like this. And for D2 scenario, this will be something like this. So this is LiFi alone. This is D1 scenario, and this is D2 scenario. So let us see at some point, say 30 megabit, for example, 30 megabits per second. So basically, you can draw and find out the CDF value for each one of them. So suppose this is 0.1, this is 0.2, this is 0.35. So basically this curve tells me that for LiFi standalone, %65 of the users, which is 1 minus 0.35 actually, which is 65% of users, get more than 30 megabits per second. If you consider the D1 scenario, 80% of the users get more than 30 megabits per second. And if you take the D2 scenario, where you dynamically allocate resources, power and spectrum, 90% of the users get more than 30 megabits per second. So one thing is very clear, if you compare with standalone LiFi, this coexistence of LiFi and Wi-Fi, that is a hybrid network, they perform better. We have seen one parameter of throughput here, and within coexistence, there can be different algorithms. We have discussed, two algorithms here, D1 where equal resource sharing and D2 where dynamically resource sharing depending upon the traffic requirement or traffic demands. We have seen the performance of LiFi, Wi-Fi coexistence is much better as compared to standalone LiFi and Wi-Fi for that matter. So under this, in this topic, there is a tutorial also as one of the lectures where the TA has explained how this scenario can be simulated, what are the tools used, how you can, do the simulation and find out standalone LiFi, standalone Wi-Fi, and coexistence of LiFi, Wi-Fi, the different parameters. So this is also included in this course, which will be taken by one of the TA, a PhD student who works in this particular area. Thank you.